Okay, this covers material in Chapter 4, Option Pricing Models. Specifically, the model we're looking at today is binomial, the binomial model. Originally derived by Cox, Ross, and Rubenstein, sometimes called the CRR model. It's been around for a while. It gives, the reason why we're looking at this model first is it gives us a ton of intuition on how to value options. So in the last chapter that we had covered in Chapter 3 on boundary conditions, we had just that, boundary conditions. We didn't really figure out, well, how do you actually figure out the call value, an exact call value of $3.28, for example, or a put for $3.28. How do you actually come up with it? I mean, we looked at boundary conditions, we looked at put-call parity, but in a lot of those cases, we were given numbers, we were given a put or a call price and just backed in to into the other, the missing variable. But but if you have a call price and you're missing a put price, where does the call price come from? That's what this chapter is about. This chapter is about actually pinning down the value of an option. And the chapter, what's really cool about the chapter is we're going to utilize no arbitrage conditions. And so we're going to value puts and calls. We're going to employ hedging techniques. We're going to use a covered call ideas and protective put ideas. We'll check our work using put-call parity, and then we'll discuss how to handle dividends. That's just the start. There's other things that'll pop up throughout this video as we go further into the material. So we're going to head through as far as, I believe, section 4.3b. I think that's as far as we go. Look at my notes here. Yeah, 4.3b. And so the best way to handle this binomial option pricing and to go through it is an example. And so here's the outline for the example. We're going to use a binomial model, and we're going to set up this, it's called lattice work. And so before I get into this lattice work, let's look at the setup here, what's given. So we observe a stock price, say on the New York Stock Exchange for $50. We know there's an option out there for 52, strike a 52. T is 1 year. And we're going to look at, now here's things you haven't seen before. We're going to look at a U. We're going to look at the how much can the stock go up in a particular step? And how much can it go down by a particular step? And what I mean by that is, look, we have a whole year, and that's what this lattice work covers. It covers today, right here, 6 months from now, here, 6 months from now, and then another 6 months, and at the end is the 1 year mark. So there's 2 steps. N is 2 steps here. We're going to label the steps N. The interest rate is 8%, but interest rates are always on an annual basis, so we're going to chop it in half to 4% per 6 month period. So this is a 6 month period, and then this is a 6 month period. And so what we have is we have a stock price today of $50 as given. And what we're saying, what this U is saying is, look, the stock at this point can go up. You basically multiply it by 1.171. In other words, the stock can go up 17.1%. And that would mean in 6 months from now, the stock would be $58.55. Or the stock can go down and you multiply it by 0.854. In this case, the stock would be $42.70. What you should keep in mind is that's just the up movement. And if you take the reciprocal 1 over 1.171, you'll get, 0.854. So I'm breaking into this video and interrupting it to cover an important point that I cover further on in this video, like about an hour and 40 minutes later or more. I cover this point right here. And I want to cover it right now to make sure that we're on solid footing. And so the question becomes, where did I get this 1.171? It kind of comes out of thin air. And then I have it, and that's U, by the way, that's U. And then I have a D, which is equal to 1 over 1.171, or normally D is just 1 over U. Okay, so where did I get this thing in the first place? Well, it's coming from sigma. It's a function of the volatility of the stock. So you get the volatile stock. The more volatile the stock is, the more likely it's going to go up or down, right? And so what we're doing is we're going to link this volatility, how wiggly the stock moves over time, and we're going to link it to these up and down moves. But how do we actually do that? Well, there's a trick to it, and the trick is going to be helpful and insightful, especially when we get to the next chapter with the Black-Scholes model. But for now, what you need to know is this is the formula that'll get you to wherever you want to go in these problems. And that is U, okay, the up movement, is going to equal E to the sigma times the square root of T over N. Now that looks like a big ugly formula. It's not that bad. This is volatility in decimal form. Okay, so this is like a standard deviation of, a 25% standard deviation. That's 0.25. So you'd plug 0.25 in here if I give you the volatility of standard deviation of the stock. T is the time to expiration measured in years of the option. And N is the number of steps. So I'm giving you, in this case, I'm just showing you a one-step binomial. And when we get back to the regular part of this video, it's a two-step, right? And you can have a three-step and a four-step. And then not only that, but you can change the time, right? You can change, well, is this 1 year? This is 2 years, and so on. Well, this adjusts to no matter what happens, no matter what the expiration is, T, you got it in here, takes it into consideration. N is the number of steps automatically taken into consideration. So if you had a 1 year option, right? If you had a 1 year option with 3 steps, it would be the square root of 1 for 1 year over 3 steps. And you'd multiply this by sigma. Now, that may still seem a bit abstract, so let me try to make some sense out of it in terms of what we just covered. Now, U equals 1.171 is what I gave you. And now I'm saying that has to equal E to the sigma times the square root of T over N. And this guy right here is in this problem that I'm about to show you, and I just started. It's 1 year, 2 steps. This turns out to be square root of 1/2, 0.7071. Okay. So now, all we have to do is solve this. U equals 1.171 equals E to the sigma times 0.7071. Oh, that seems like a nightmare. How the heck do you solve for, really what we want to do is we want to solve for sigma. Because what I'm saying is if I give you a U, it implies a sigma, how volatile the stock is. And so what we do is we take the logarithms of both sides. If you look at your calculator, I don't know how clearly you can see that here, but if you look at your calculator, there is a log button, natural log button right here. It's kind of glary. Natural log button, and then the second to the log gives you E, if you can see that there. And so that flips between logging and unlogging variable. And so what we want to do is we want to take the logarithm of both sides, and when you take the logarithm of both sides, this no longer becomes an exponent. And let me show you. It's going to be the log of 1.171 equals the log of E to the, well, let me just simplify it. It's just going to be sigma times 0.7071. Okay? All I'm doing is taking this exponent and bringing it onto this side, get rid of the E. So now if you take the logarithm of 1.171, you come up with 0.15786 equals sigma times 0.7071. Solve for sigma like it's an x. And sigma comes out to be 0.2231. Aha! That's the standard deviation of the stock, of the underlying stock, 22.31%. So the point is, you can be given a U, and if you're given an up movement, you can, it implies, and you can back into what the volatility of the stock is, the standard deviation of the stock. Now, if you're given a standard deviation of a stock, which is what most people in the real world use, they don't care about U's. You don't hear people trading on U. They trade based on standard deviation of the volatility of the stock. So you're given this, well, with this formula, you're given sigma, and you know the time to expiration, and you set the number of steps in the problem, then you can figure out what the U is. So you can go back and forth. So in the text, let me come over here. U in the one case is 1.25. Well, that doesn't mean much until you realize the context of the problem is that it's going to imply a sigma, and that there is a time period, which is a time period till expiration of that option. And he started out with one step. And so this kind of disappears pretty quickly because the square root of 1 over 1 is 1, and the square root of 1 is 1, obviously. So this the math simplifies pretty quickly. And what happens is you take the log of 1.25 equals sigma. And the log of 1.25 happens to be 0.2231. And so sigma here equals, this is sigma equal 0.2231 here. So why are these two things the same? Well, this is what's going on. If in the textbook he's using 1.25 as a U with just one step, and I'm in my problem, I'm doing a two-step model with U equal to 1.171. What that means is we're looking at the same stock with the same underlying volatility. So he's using a U of 1.25 in a one-step model, and that implies a volatility of about 22%. And then I'm applying it to a two-step model in a one-year two-step model, and I'm getting 22%. That means it's the same underlying stock, and we can model it with just a 1 year. We can model it with just one step. We can model that 1 year with a two-step. Doesn't matter how you model it. This stock has the same underlying volatility. We're still working with this $50 stock, which is today, and it depends on how we model it out into the future as to whether we want one step or two step. We could do three step, and if we did three step, it would be e to the sigma square root of 1 year over 3, and that would be and we would get a new U for that if that was the case. But I wouldn't go there. I'm going to stick to two-step models, because I think once you get through two steps, you get all the intuition you need. One step, you kind of miss out on the intuition. You really need the two-step model at a minimum. If you go three steps, look how crazy it gets. If you go three steps, you got to go out this way, this way, this way, this way, this way. It just becomes too much math, and you get lost in it. So I compromise and stick almost always to a two-step model in my explanations. But when it comes to quizzing time, I sometimes just do a one-step model because it's even simpler. Because I assume that if you can do the one-step, you can do the two-step. I hope that makes sense. So to reiterate even more, if I give you a U, it implies a sigma, and you got to have the T over N, so you got to know that to solve the problem. So this will be given. And if I give you a U, you can solve sigma. If you're given a sigma, you use this formula. Plug the sigma in, use this formula, and you can calculate U. And once you have U, you can start going your up and down, doing your up and down movements. I hope that helps. The point is, you're sitting here at time 0. The stock can go up or it can go down, and this is the prices going up and going down. And so what we want to do here is we want to fill out this lattice work for the stock price all the way to expiration. And that's why I have the S here for stock price. So we have a binomial, up or down. Two ways you can go. You can't go any other direction or any other way. There's just up or there's down. So you go up the first step, and then when you're at this step, the stock can go up another 1.171, another 17%, or it can go down basically around, around 15% drop is basically what's happening here. So the stock can go up to 68.56 at expiration if it goes up and then it goes up again. If the stock goes up and then it goes down, multiply these two numbers together and you get a 50 here. Notice the 50 matches up with the 50 we started with. Comes up, comes down, up, down, and then up. This is what's called a recombining tree because it combines here. If we would have a non-recombining tree, by the way, would look like this. A non-recombining tree would look like this lattice work. And non-recombining trees are okay. You can value options with the non-recombining, but you basically have an extra step because instead of having 3 nodes at the end, you have 4. And so it's more mathematically involved, especially as you go further out in time. So in this particular example, to get the context right, we're only looking at an option that lasts 1 year, and we just assume that we're doing 2 steps. The textbook jumps, as most textbooks jumps right, starts with a 1-step model and then builds on 2 steps. But why not just combine it, and we'll just start out with 2 steps. You can do 3 steps, 4 steps, but trust me, once you get past 3, the math is just too cumbersome after a while. So the point is, keep it to 2 steps and we'll get all of the intuition that we need from these 2 steps. So let me continue filling out the lattice work. So the goal at the moment is to fill out the lattice work for the stock price. And so we have one more stock price to fill out. We need to multiply this 4270 by 0.854. And so the stock price going down twice would be 36.47. Okay, so we just picked these numbers. They're, somewhat reasonable. The stock can go up 17% or it can go down 15%. And we figured out stock prices all the way through the end. Now, you might ask, well, what is our goal in all of this? Our goal is somewhat, I'll say it simply. Our goal is we want to know what is the value of the call right here. What is the value of the call today? Or what is the value of the put today? What is the value? And from this stock lattice work, we're going to back into what the call should be today and what the put price should be today. Okay? And we have a lot of the intuition already. And so let's start by figuring out what the value of the call should be at expiration, which is this column right here. And then we're going to work backwards through the tree to come up with the call price today. And so I'm going to try to keep this as clean as possible so I don't write all over it. Let me show you how to calculate the call value right here. So the call value at expiration, the call value is the maximum of 0 or the stock price minus X. And in this case, the option is certainly in the money because the stock is at 68 and change when the strike is at 58 or 52. 52 strike. So that means this is 68.56 minus 52. This is in the money by 16.56. In other words, it's in the money. And that is the payoff, and that is the value of the option at expiration, if this happens. When I say this happens, if stock goes up once and then goes up again, stock will be 68.56 at expiration. That implies the call must be 16.56. Okay, let's figure out the call price here. Now, really, we don't have to do any math because the option is out of the money. Because you wouldn't want to buy the call for 56 when it trades in the open market at 50. So this option is out of the money. And the same here. When the stock falls far low, the option is out of the money. So we just figured out the option values under these three scenarios. Now the next step is, what is the option value here? Call it CU. And what is CD? Where CU means what is the value of the call when it goes up once? Okay? And what is the value of the call when it goes down? And what we're going to do is we're going to, using this information from these two prices, we're going to converge down to this CU. We're going to look at these two prices. We're going to converge over to the CD, get these numbers, and then we're going to work backwards again to come up with what the call should be here. So we're working backwards through the tree. Now, let me give you the underlying intuition of how to set this up, okay? Of how to compute the call on the up and how to compute the call on the down side. So let me do that. It's rather, it's a bit involved. Some of the notation will get is quite cumbersome, but bear with me because I'm going to keep going over the same routine, so to speak. I'm going to determine this value from these two, and then I'm going to determine this value from these two, and then I'm going to determine this value from these two. It's very repetitive. So after a while, you won't need the notation, but I need to show you some of the notation so you keep up with what the textbook is describing. The textbook goes into detail on how to do this, and I'm trying to cut it down to as simple process as possible, and so that you can get the intuition out of it without too much complications in terms of symbols. So I'll show you some symbols up front, and then after a while you'll see, I don't need the symbols anymore. I'll just chug the numbers and to come up with the values. So our goal here now is let's figure out what the call is on the upside. Well, the way we're going to do that is we're going to put together a portfolio so that the value of a portfolio of a stock and a call on the upside. So we're going to look at the value of a portfolio of a stock and a call on the upside going up twice versus the value of a call and a stock when the stock goes up and then it goes down, or it could be down or up because it means that it results in the same thing. So what we're saying is, let's create a portfolio. We're going to create a portfolio here at this point in time. And the value of the portfolio will be VUU at this point, the value going up, which means it went up twice, where the value of UD of this portfolio of a stock and a call, because you went up and then you went down, which is the same as saying the value going down then up again in a recombining tree. So we're looking at these two values, and what we want to do is we want to, at this point, put together a risk-free strategy, a risk-free portfolio of a stock, certain shares of stock, as I should say, and a call option. Okay? And so we're going to put that together so that no matter which way we end up or down, it's a risk-free situation. And we do that by coming up with a hedge ratio labeled H, little h. And let me proceed with it and then I'll explain. So we're going to set up, we want the value of our portfolio to look like this. So here we have a stock. Now let's get the symbol straight in the text. Well, the text uses, okay, I think it's U squared in the text, meaning the stock went up twice. So we have this stock that went up twice, and that's what this is, 68.56. The stock went up twice. We're going to multiply it by H. okay, H shares of stock that we have, okay? And we're going to subtract out a call when the value, and that's the value of the call when the call goes up twice, okay? Which again is labeled U. Let me write that over so it's clearer. It's U squared SH minus CU squared. And so that's how your textbook presents it. That just means U, two ups, two ups. Okay, so now what we have is we have a portfolio here of a certain number of shares of stock, H, times the stock price of that's gone up twice. We're going to subtract out a call that has gone up twice. So we're right here, like I said, we're right here in this situation. We want to set the value of the portfolio here equal to the portfolio down here. And so we want that to equal UD S, so that's the stock price going up and then down. And we're going to multiply that by S, the stock, by H, the hedge ratio, minus CUD, which is the value of the call when the stock goes up and goes down. We want to set these two portfolios equal. Now, if you look really closely at this, you know what we have? We have basically, it's a lot like a covered call. So notice we own a stock because it's positive. We own a certain number of shares of stock here. And then we wrote a call. See the minus sign? That means we wrote a call. So what we're doing is we're using the call, the shorted call, and the long stock. We're hedging against each other. They're offsetting each other. And we can offset it so that no matter what happens, if we go up twice or we go up and then down, we're going to have the same value of a portfolio, because this right here is a portfolio value. That's why it's labeled VUU. And then we have the value of the portfolio when it goes up and then down. Well, that's this value of the portfolio. So what it's saying is if we figure out the right number of H, the right number of shares, then we'll be able to figure out when this portfolio exactly equals this portfolio, the portfolio up versus the portfolio up down. So if you rearrange this, and solve for H, you end up getting a nice exercise for you to do. H is calculated as CU squared minus CUD, and then it's U squared S minus UDS. And that equals, okay, we can figure out what H equals. H equals, plug the numbers in. This is 16.56 from this table. And then it's going to be 0 here for the CUD. Okay? And then what we're going to do is we're going to take the stock on the upside, 68.56, and subtract it on the downside, 50. That means H is going to be 0.892. H will always be equal to 0 to 1, somewhere between 0 and 1, including 0. It could be 0 and it could be 1. So it's somewhere in between there. Here it's 0.892. Now I'll give you an interpretation of what H means in a second, besides the fact that it's a hedge ratio, and that's why it's labeled H. Okay. So let's continue now. And so now what I'm saying is if we have just under 1 share of stock, then the value of the portfolio going up will equal the value of the portfolio going down, or up and then down. Okay. Now let's go another step further and let's form a riskless portfolio. And this riskless portfolio we're going to form is we're forming the portfolio right at this point. And so it's riskless, meaning it doesn't matter if we go up or it doesn't matter if we go down. Because why doesn't it matter? Because it doesn't matter if we go up and then down from that standpoint, because they're both equal. So if they're both equal, there's no risk involved. So let's put together a riskless portfolio. I'll do it symbolically, and then we'll drop the numbers in and calculate the value of the call. So our goal right here is to calculate that call, don't forget. The call on the upside. Okay, we're going to have US, which stands for the stock on the upside, times H shares, the H we just calculated, minus the call on the upside. That's what we're solving for. We're solving for this guy right here. Okay, this is a covered call, basically. And this covered call, since we're going to create a riskless portfolio, this is going to be riskless, well, then it better grow at the risk-free rate. So remember in a previous video, I said, you know, if you have a riskless stock or you have a riskless, anything riskless, it grows at the risk-free rate. It can't stay constant and not grow because nobody would invest in it. So it's got to grow at the risk-free rate because there's opportunity cost involved. So we have this covered call position. This is the value of the covered call position. It's going to grow at the risk-free rate. And we need to make one little adjustment here. Since we have a two-step process, we need to divide the rate, the annual interest rate, by the number of steps in the binomial here. And remember, the binomial has two steps, and so R is basically, R divided by N is going to be 4%, as I told you up front. Let's continue. So this is the riskless investment that we're forming. And the riskless investment can go either to this value or this value. It doesn't matter because we just set them equal by having the right number of shares, the optimal number of shares in the hedge ratio. So what I'm going to do is I'm going to set it equal to this side. It's easier because this call is going to be 0. And so the math is a little simpler. And so we're going to look at it this way. So it's UDS H minus CUD. So that's it symbolically. So we have everything we need to solve for this guy. It's one equation, one unknown at this point. So let's solve. Plug the numbers in and solve. The price, US, is the 58.55 right here. 58.55. The H is 0.892, as we just calculated a minute ago. Minus CU is what we're solving for. This is 1 plus 0.08 divided by 2. In other words, 1.04. That equals the stock when it drops, when it goes up and then drops. In this case, it just goes down to here. That's going to be 50 times the 0.892 minus the call. When the stock goes up and it goes down, the call is going to be 0. So it kind of makes the math a little easier when you pick this side here rather than this side in this example. Now, when you solve for all of this, and that's really not that hard, multiply it out, bring this over, you end up with CU equals $9.35. Wow, so look what we just did. We just solved what the value of the call is in this situation. So if we're sitting here and we go up once, what is the value of this call? Well, given the conditions that are going to happen one step ahead, as we predicted, the value of the call should be worth $9.35. Now, let's look at CD. What is the value of the call on the downside? This guy. What is this right here? Well, we don't have to do any math at this point. And the reason is, no matter what happens, if you're sitting here, the value of the call is 0 or the value of the call is 0. So the value of the call has to be 0 here because it doesn't amount to anything in the future, no matter what happens. So we can reason that out to be 0. And then we'll just plug in a 0. So now we know the two call values here at the first step. Now we're going to repeat the same process I just did and bring these back to figure out the call at time 0. So I'm doing the same process. Okay. we're going to look at the value of a portfolio on the upside has to equal the value of the portfolio on the downside. Okay, after one step, the value of the covered call position should equal. And so that's USH minus CU equals DSH minus CD. Plug in the numbers and solve for H. Okay? If you plug in the numbers, solve for H, we plug in the numbers we just solved for CU and CD, by the way, and that's going to be, it's going to result in solving for H. H equals 0.59. Okay? That's the new hedge ratio. So the hedge ratio changes at each node on the tree. Each node of the tree, the hedge ratio changes, by the way. So keep that in mind. So now what we're going to do is we're going to form a riskless portfolio. And we're going to form the riskless portfolio at this point in time so that the riskless portfolio, if we have the right number of H, okay, the right hedge ratio, 0.59, it doesn't matter if the stock goes up or the stock goes down, because we've just set these two values of the covered call position equal. So we don't care if it goes up or down. We basically have a riskless portfolio. And so we're going to write that out as, here's the stock at time 0 multiplied by H minus the call price today. That's what we're solving for in this formula. What is the call price right here? So that's what we're going to solve for. This portfolio is going to grow at the risk-free rate, like I showed you before. And that, divided by n, don't forget, the risk-free rate divided by n, 2 steps. And that is going to equal the stock price when it goes down times H minus CD. And again, I did this, I picked this side only because I know CD is 0 and it makes the math a bit easier, a couple of less calculations. And so if we put in $50 times 0.59 minus C subscript 0, this is 1.04. This turns out to be 4270 times 0.59 minus 0. And so when you solve for this, the call is worth $5.28. Aha! The call is worth $5.28. Okay? So now let's look what we just did. Given this information up here, I was able to determine the value of this option at $5.28, given the situation. Now I know what the stock price is, X, T, R, the risk-free rate. I choose the number of steps. And by the way, the more steps you have, the more accurate this number comes into. So this call price of 528 is an approximation and depends on the number of steps we choose. If we do an infinite number of steps over 1 year, we would come up with an exact dollar amount for that call. But I could tell you just going to 3 steps, the math is crazy. It's not worth it. But what I'm showing you is just 2 steps gives you the intuition on how to value a call. So what did we do? We looked at we used a covered call type strategy, which means the stock is bullish. We're using that shorted call and we're kind of using them against each other to form riskless portfolios. In other words, we're using the stock's ability to hedge, the option's ability to hedge the stock in order to price the call option. So a call option is a function of its ability to hedge the stock. That's what this is saying. It's what's between the lines of all this. I'll say it again. The value of the call option is a function of its ability to produce a riskless hedge on the stock. In other words, insuring the stock. And so, using those procedures, we come up with $5.28 as an approximation at this point. The next chapter, when we do the chapter on Black-Scholes option pricing model, that model embeds an infinite number of steps. And so it comes up with an exact price. We're not going to use binomials in that chapter. But we can come up with an exact price, not an approximation, because the math condenses down, and the math is kind of, it's a little rough, but it condenses down to an infinite number of steps. So now where we stand is, okay, we just valued the call. Let's value the put today. What is this put worth today? And so I've already outlined what we need to do here. We need to value the put at the end, at expiration, and then we're going to take these two puts and we're going to bring them back to come up with a put right here on the first up node. And then we're going to figure out the put on the down node using these two put values. And then we're going to do the whole thing over again, and we're going to take these two puts, we're going to bring them back till we come up with this put value. Okay? So it's repetitive. And so the formulas I don't think are worth looking at or using, because once you get the hang of it, you don't need the formulas anymore. So let's value the put. Now, by the way, we're dealing with European options here. I didn't mention that earlier, but this is a European. So just keep that in the back of your mind. So now, let's look at the value of the put here. Now, you know the formula for a put at expiration. The value of a put at expiration, remember, is the maximum of 0, or x minus st at expiration. So there's no discounting because there's no time left, all right? So it's x minus st. So in this case, when we go up, stock goes up and it goes up, then this is going to be 52 minus 68.56 versus 0. So this means the maximum, or the intrinsic value of this option, is 0, which makes sense because when stocks go up, puts tend to not have value or lose in value. And so the put has no value. It's out of the money at this point. Now let's figure out what the put is on the middle node. Well, in the middle node, it's the maximum of 0, 52 minus 50, which equals 2. So the put here is 2. And then the put for the bottom node is the maximum of 0, 52 minus 36.47. And that equals, I've got my numbers here, it equals 1553. So the 36.47 came from the stock price here on a down move. So this is going to be 1553. So wow, we just figured out there's a chance the option finishes out of the money, there's a chance that the option finishes at 2, and there's a chance that the option finishes at 1553. There's no other possibilities in this binomial. These are the 3 chances that can happen. So what we want to do is, again, let's work backwards through the tree, figure out what the call is on the upside, figure out what the call is worth on the downside, and then we'll go back to time 0. Okay, so what we're going to do is we want the value. Let's see if I get my calculations here. We want the value on the upside going up twice equal the value of going up and then down. So the point is, we want the value of a portfolio with the stock and a put. So no matter if you go up or you go down here, from this point of view, if you go up or you go down, the portfolio is the same value, assuming we have the proper optimal hedge ratio. So let's calculate a hedge ratio for the put. Now keep in mind the hedge ratio, as I said, changes with every node, and there's a hedge ratio for the call and there's a hedge ratio for the put. So we want to calculate what that hedge ratio is going to be. And so we're going to put together the stock price here, and I'm going to try to get rid of as many symbols as I can, times H. So so this is the stock on the upside twice, times an optimal H, plus the put. So right here, the 68 and the 0. I'm using those two numbers to come up with the 68 and the 0 here. So that's the portfolio. And by the way, notice what I'm doing is I'm taking a certain shares of stock plus a put option. Wait a second, we've seen that before. That's basically a protective put. We're using the stock and we're hedging it with a put. So we're kind of offsetting. We're using one to offset the other. So we're using a put to hedge the stock. And when we do that, we can value the put option using the protective put concept here. So now what we want to do is, what is the value on the downside, up and downside, which is right here? What is the value here of this portfolio, this protective put? And that value is going to be $50 times H plus 2, because when you buy a protective put, you buy the put. So the value is plus 2. So this is the value of the portfolio on the up downside. This is the value of the portfolio up upside. Solve for H, and H equals 0.108. Okay? 0.108. Now form a riskless portfolio. And we're going to form the riskless portfolio right at this point in time on this node. What is the riskless portfolio? So this riskless protective put. So no matter what happens, if the stock goes up or the stock goes down, the riskless put pays off the same amount. If it pays off the same amount, there's no risk to it. So, and that's why it's a risk-free portfolio that we're putting together here. So we're going to take the 58.55, that's the value of the stock price on the upside, multiply it by the 0.10H, the hedge ratio, plus PU. That's what we're solving for. We're solving for this. It's going to go up by the risk-free rate, chopped in half because there's two steps. So this portfolio, which is riskless, this portfolio right here, it's riskless, is going to grow at the risk-free rate, and it's going to equal the value of the portfolio. If it goes up or it goes down, it doesn't matter. Let's pick the upside because the P is 0. The put is worth 0, and it makes the math a little simpler. We could have set it equal to this scenario, but we'll set it equal to this scenario this time. So it's 68.56 times 0.108 plus 0. And now solve this mathematically for PU. PU equals 0.80. Oh, okay. The put on the upside at this point in time is worth 80 cents. Great. Now, let's do the put on the downside. So we got to form a riskless portfolio. Well, first of all, we're going to form a riskless portfolio. So if we go up or we go down, we end up with the same value. And then given that, we're going to back into what the value of the put should be on the downside. So rewrite the math here. We're going to take 50 times H. Let's come up with a new hedge ratio. Plus 2 equals 36.47 times H plus 15.53. Okay, so I'm using the numbers right here. It's these two numbers, and then I'm using these two numbers here. So if we have the right number of shares, it doesn't matter if we go up or we go down, we're going to have the same portfolio value. And the H here is exactly 1.0. Okay, the H is 1.0. So let's set up a riskless portfolio that grows at the risk-free rate. It doesn't matter if it goes here or it goes here. So 4270, we're starting that riskless portfolio. The portfolio we're putting together starts right here, and it grows to this amount or this amount for a protective put. Times 1.0 that we just calculated, plus PD. That's what we're solving for, that put. It's going to grow at the riskless rate, and it doesn't matter if it equals this or it equals this. I'll pick the 3647 times 1 plus 1553. Solve for PD, and PD equals 7.30. Okay, $7.30 is what that put. Now notice the call makes sense here. So if you compare, the call is worth more than the put because the stock went up. And down, when the stock goes down, the put is worth more than the call. You notice that. And you can also notice it on down this dimension. So now, if you follow the same procedure, follow the exact same procedure, you'll come up with the put today, which is ultimately our goal. We want to know what is the value of this put today. The value of this put today is 335. And let me show you how to calculate that put at 335 is. We're going to set up a riskless portfolio. So set up a riskless portfolio so it doesn't matter if we go up or we go down. And then we're going to divide, we're going to back into it, we're going to create another riskless portfolio that grows at the risk-free rate. It doesn't matter if it goes up or down because it's worth the same value. So 58.55 times H is what we're going to solve here, plus 80 cents that we calculated a minute ago. 42.70 times H, which is what we're solving for, plus 7.30. H equals 0.41. Okay? Now, create that riskless portfolio. Oops. Okay, that's a times. Plus P subscript 0. That's what we're solving for. This has to grow at the risk-free rate. And it's going to equal, it doesn't matter if it's this side or this side. And I'll pick the upside, 58.55 times 0.41 plus 80 cents. Solve this out, and the put is worth 335. And there you have it. We just figured out the call and the put for these for these options, for this lattice work here, for this stock. That's the call, that's the put. Now, before you go any further, we just did a pile of math on this, so you can see that. I got so many pieces of paper here, I can't keep track of it all. But now what we need to do, and this is, text doesn't do this. I want to show you that we can verify our work because, like I said, we did a pile of calculations here. How do we know we didn't screw it up? So the way we check is we go put call parity. The call minus the put, because we just calculated those two guys, and we have the stock price, and we know what the strike is, and we know what the risk-free rate is, and we know what the number of steps that are involved. There's 2 steps, 2 periods, n equals 2 in this case. So we have all this information. Does this side equal this side? And if it does, put call parity works. This equals $1.93, the difference between the two option values. 50 minus, see the 1.04 squared? That's basically, almost about 8% discounting back. And that equals $1.92. I mean, so we're really close. We just have rounding differences. So, after all that work, all those calculations, we can be pretty comfortable that we did the math right because put call parity worked. Now that's amazing. You see, amazing because we didn't, that we can check our work in that way, but it is a really nice way to check things. Now, let's go further. Now, I said before, let's do an interpretation of H. Let's do an interpretation of H. There's 3 ways to interpret H. Okay? So the first way is it's the number of shares of stock, in this case, needed to replicate a risk-free portfolio. So we created a risk-free portfolio with just the right number of shares of stock, H. Now here's a little warning for you. If you go to other textbooks or you go to the web and you look up binomial option pricing, you'll find 1,000 videos on it. But some people, some texts calculate a hedge ratio, not on the number of shares of stock like we did. See, we applied H to the number of shares of stock, and we had one option all the way, one option with H shares of stock. Some websites and some authors use H they use fractional call options and use 1 share of stock. They use 1 share of stock, but fractional options. So the H ends up on the option. It's not the way it's done here. It's H shares of stock, 1 option. So that makes it easy because what we want to do is we want to value 1 option. So it makes it way easier if you want to value 1 option to put H on the stock itself. Okay, so that's really by definition the way we used H. Now here, the next interpretation, I'm going to say roughly now, roughly. It's an approximation for the actual probabilities of the stock finishing in the money. Okay, it's roughly an approximation for the option finishing in the money. Well, let's see. Let's see if that makes sense. If you recall, I'm going back. H here was 0.892. H here, and that's for the call, by the way. H here was 0 for the call. Okay, now let's interpret. Now for this H being 0, that means the probability of the option finishing in the money must have been 0 at this point. Well, it was for the call because no matter what, the call went to 0 or it went to 0. So the probability of the option finishing in the call, or in the money for the call, was 0. Okay, that makes sense. Now the probability of this option, call option, finishing in the money at this point, it either goes up to 1656 or it goes to 0. And we're saying there's almost a 90% chance that that option is going to finish in the money at the 1656, and about a little over a 10% chance that it's going to be 0. Okay? And then we figured out, what did we figure out? The H here for the call, I'll put a little C there, was 0.59. So what we're saying is, at this point, the probability of the option finishing in the money here was 59% at that point. That's roughly, okay? So that's one way to interpret it. The third way to interpret H is it's the slope of the option price profile. Now, I occasionally use that word profile. This is what I mean. Option pricing profile is this. Remember, we had the lower bound at expiration looked like that for a long call. And then we had a call option that kind of looked like this. The actual call value. And by the way, that's exactly what we're doing here, by the way. Let me see if I can drop the numbers in. This was 52, and the stock was at 50. So we're saying the call option at this point was worth $5.28. So we pinned it. Remember I told you, this is pinning it right down to the dot there. That's what it's worth, $55.28 when the stock is at 50. Okay. Now, the slope of this line, this profile, this curved line is often called a profile. The slope, in other words, what is the slope of a tangent line right next to it? That's roughly h. So when we looked at this model right here, h is about 0.59. That's the slope. The slope here starts out at basically 0 here and approaches 1. Remember I told you that this slope is positive 1, so this is approaching that positive 1 slope. So you can see h goes from positive 1 to 0, and so it's giving you an indication of the probability the option finishes in the money when you have this slope. So there you have it. You have three neat interpretations. It's the number of shares for replication of the stock. It's roughly an approximation for the probability of the option finishing in the money. Well, I should say here, the stock finishing in the money, yeah, it's really the option finishing in the money. And then it's the slope of the option price profile. And so when you have an H, when you're computing your H's, you need to ask yourself, does that H make sense? If I'm way up here with the scenario well above the strike, my H should be close to 1. If I'm over here, my H should be close to 0. So remember what an H of 0 is telling you. The stock price can change a lot at expiration, but the value of the call barely changes here. And here what we're saying is there's basically a 1-to-1 change for the option price versus the stock price when you're way up in the money. And when you're close to the strike, you're somewhere in the middle. And there we have it, 0.59. Now what I want to cover is risk-neutral probabilities. Now, we haven't addressed probabilities at all in the model so far. We are now. Risk-neutral probabilities. Now, when I'm talking about risk-neutral probabilities, there's no risk premium. We are dealing with, this is a bit tricky to wrap your head around, but we're dealing with risky assets. A stock by itself is risky. You know that. A call by itself is risky. A put by itself is risky because, it could go in or out of the money at expiration. So it's risky. A stock can go up or down. It's risky. But we are in a position now to look at risk-neutral probabilities. There's no risk premium because we had no risk. We formed a riskless portfolio with, by solving for H and getting just the right number of shares of stocks that we created riskless portfolios. We kind of extracted the risk out of the problem. And so the easiest way to wrap your head around why we're looking at risk-neutral probabilities is because we have no risk in the situations we just put together, whether we did a protective put and valuing the put or a covered call strategy with valuing the call. But implied in this whole process, in this tree, are probabilities. Now, we don't work with any probabilities. Probabilities don't show up anywhere in here in these calculations. But I'm going to introduce them now because what I'll show you is a really nice shortcut, a simple shortcut. Now, it's a shortcut, but you're going to lose all of the rich intuition I just showed you with developing the tree and hedges, and how an option can be valued based on its ability to hedge the stock. So let me jump into risk-neutral probabilities, show you the shortcut. Now, you can look at it in two ways. Here we have a stock price today. Stock price today equals the discounted expected value of the stock price one step away. So you can think of it as the stock price of 50 right here is a weighted average of these two stock prices here. And then we have to discount it back 6 months to come up with the $50. So what we're saying is there's a probability. I'm going to use the notation PR because the text uses P for a put value and P for the probabilities, using one's cap and one's lowercase. I can't really draw that out. So I'm going to use PR for probability, so you know it's not a put option value. It's a probability. So PR times the stock price today times U. Okay, if you recall, that's US. That's US right here. The stock price times U is the US plus 1 minus the probabilities, because the probabilities have to add to 1, and when you have PR, 1 minus PR forces the probabilities to add to 1, times the stock price today times D, the down node. And then we're going to, that's the expected value of the stock price 1 period from now, because the stock can go up, the stock can go down with those probabilities, and we're going to discount it back. Well, in this case, 1 period. We're going to discount it back 1 period, because that's what we're looking at, just 1 period. These two prices discounting back 1 period. Okay, so if we look at it this way, why don't we, when you look at this math, why don't we cross out the S's? Because S subscript 0, S subscript 0, and S subscript 0 means if we divide both sides by S subscript 0, we get 1 equals the probability of up plus 1 minus the probability going down divided by 1 plus R to the N. Solve for PR. And PR equals 1 plus R to the N, the risk-free rate minus the down divided by U minus the down movement. Okay, so that is the risk-neutral probability. Okay? And that risk-neutral probability can also be solved for with, right here it's a little smaller. You can take the call today and look at it as the probability of the call today going up plus 1 minus the probability of the call going down divided by 1 plus Rn to the 1 power. You can also look at it that way, cross out the C subscript zeros, and you get 1 equals PR U plus 1 minus PR times D, all divided by 1 plus R to the N. And what you end up getting is you get the same probability. Okay? Same probability. You can derive it from the stock, you can derive it from the call, because at this point, both are riskless, because we just put together a riskless hedge. So the probabilities, risk-neutral probabilities, apply to the call, apply to the stock. And so what is that probability? Well, before we go anywhere, let's make sure that that probability better be between 0 and 1. Okay, so let's look here. 1 plus 0.08 divided by 2 minus 0.854. 1.71 minus the 0.854, that equals 0.587. 0.587. And by the way, that probability remains constant across the tree. So remember, when you go across the tree, the H's change. There's a different H, and it changes. And sometimes it's, what we're doing is we're looking at dynamic hedging. And that's sometimes what this is called, dynamic, because we're going through time and we're changing the hedge ratio based on conditions. And those hedge ratio changes with a call, it changes with a put. But the probabilities of going up or down. So this PR is a probability of an up move is 58, almost 59%. So the probability of going down is 41.3%. And by the way, notice this probability is almost 59% of the option going up, or the stock going up. And that's basically what the hedge ratio was. So when you're sitting at this point in time, so when we're sitting at this point in time, we're saying, what's the probability of the option finishing in the money? Well, the only way it could finish in the money is if the stock goes up. If it went down, it was out of the money with a 0 here. So the 59 and this risk-neutral probability is no coincidence that they're about equal. Okay, so I told you it was an approximation, and there we got it. We got it from another angle, that risk-neutral probability. Now, keep in mind one more thing before we move on. You can take, now that we have this risk-neutral probability, I'll tell you how to do it, and hopefully you can do it at home. I'm going to explain it to you. You take the probability, multiply that 59.5, let's call it 0.59, multiply it by the stock price here, multiply 1 minus that probability times the 4270, divide it by the interest rate, which is 4% for the 6-month period, you come up with a stock price of 50. The same thing with the call. Discount the call back, so you don't have to do anything here because it's a 0. Math works out easy. Multiply this by 0.59, and you're going to come up with, now I'm looking at, I was doing a bad comparison. Take the 0.59 times the $9 here, $9.35, and then take it the 1 minus the 0.59. Here's a 0, this 0 here, and discount it. And so basically, you're just multiplying this by 0.59. You'll get the $5.28. And so you could do that all the way through. You don't have to do the hedging technique to actually work this tree. You can come up with the end nodes right here. All this information is easy to calculate. We've done it a bunch of times. All you do is you plug it in to this formula. You get the probabilities, and you just count everything back. You save yourself an enormous amount of time doing that. So take it. So what I would do is, if you took 1 minus the 59 and multiplied it by 2, you'll come up with the 80 cents, is what I'm saying. Okay. Now, let's move forward. It's a good time now to talk about how I did this lattice work. As I've been saying all along, I've been doing, since the beginning of the course, I've been attempting to do things on a per share basis. So we don't have to multiply things out. And so I did that in the calculations of these calls and puts on the binomial. If you look at your text, the text, look at the binomial boxes that they have in the text. You see a lot of detail, lots of calculations of basically they're looking at 1,000 options. They're scaling everything up by 1,000 options and doing a number of shares as a percent. H is a percentage of 1,000 shares, basically, of stock. And so there's a lot of detail and calculations that really you don't need to know. I mean, what I showed you in these calculations, look, I got right to the call and the put values without having to show a giant underlying portfolio value and how it moves through time. So don't get worried about all the information that's in those boxes. Use the scaled down version, which gives you all the intuition that you need to solve for the call and put price today. Now let's take a look at an Amercan put. Now you notice, you may not catch it, but I just skipped an Amercan call. So normally I do calls then puts, but in this case I'm skipping the Amercan call. Now why am I skipping the Amercan call? Well, because we showed in the previous chapter, remember we had a discussion where we had the lower bound for a European and an American, and we said this was the American lower bound, and then we said this was the European lower bound, and we said, which was the present value of the strike, we said that, look, an American can do everything that a European option can do. So this line, this was an illusion. That's really not the right boundary condition. The boundary condition is higher for a European or for an American. It's up equal to the European. So there was no advantage to exercising an American call option early, is what that said. So there's no reason to set up the lattice work for it. For an American call, because we already did it with a European. Now, let's move on to the American put. Now, we're going to use the same setup as before. Okay, we're going to use the same setup. So let me draw the lattice work. Make sure it's recombining. and we're going to have a stock price, and we're going to have a put price at the end. We have a stock price at time 0 of 50. We have a strike at 52. Its N equals 2 steps, and T equals 1 year. So every step is 6 months. Okay, and then R equals 8% annually, or 4% every 6 months. That's the setup. So let's same lattice work here. We're going to do the same for the stock, the same lattice work. And then we're going to put the put values in, the same put values at expiration. Oops, this is a 2. The same put values as we did, because at expiration, there's no difference between an American and a European put. And so the payoffs are right listed as we did before. Now, we're going to go through the lattice work, but here's the trick with an American option, specifically here, American put. We must ask ourselves at each node where we are, is it more valuable to exercise the option or to keep it? In other words, hold it for the next step. Okay, if it's more valuable to exercise, right, then what we do is we insert along the way, we insert the intrinsic value, which is the exercisable value of the put, in place of the European put value. So why don't we put in the European values here, and I'll put in PE up here. So we know this is the upside. So this was 80 cents. And the put down here we had calculated for the European was 730. And the put for the European at time 0 was set at, we determined 335. So those are the Europeans there. Now what we want to do is we want to ask ourselves, when we're at each node, not at these nodes, at these nodes, that the nodes one step back, because like I said, a European and American puts are all worth the same at expiration. It's this payoff. Now, at this node, it's a different story. We need to ask, is it optimal at this point to exercise this put? Well, the put is, the stock is at 58.55. The exercise is at 52. It's not optimal to exercise this. It doesn't make sense to exercise it. So what we're going to do is we're going to keep this. This European price is the same as the American. So I'll just put it in there. PA equals 80 cents also. Okay? Now, let's apply the same logic coming down to this node right here. Okay? So now we ask, if we could exercise this option, should we exercise the option at this node? Well, wow, yeah, we should. The option is in the money by $9.30. That's the exercisable or intrinsic value right now. And $9.30 is greater than the $7.30. So for the put, the American put here, it's $9.30. Okay, so that's what we want to work with. We want to work with this. These are the American put values also, right here. These are American, these are American. Now let's figure out the American put today. That's our goal here. Well, we can use the logic we just learned a minute ago, that if we discount these back by the probabilities, we can come up with the price of the American. So we take the 58.7 times 0.80, add 1 minus 58.7 times 930, discount it back at the 0.082, discount it back one period, and we end up with a put of $4.14. And there we have it. The put here is worth, the American put is worth a little bit more than the European. Now let me move into Dividends. What do we do with dividends? Let me just explain them to you without going through the lattice work, because it can be a bit tedious. There's three things you can do to try to handle dividends. Three dividend, I'll call them procedures, to handle these guys. Now, there are three basically different assumptions, and so what the textbook doesn't really highlight for you is that depending on the assumption that you make on how dividends are paid and how to account for them in the binomial, you'll get different answers for a binomial call and put price. So your puts and calls will depend on the assumptions that you're making, and your assumptions will be different. You'll end up with different amounts slightly. That's worth knowing. But the three adjustments that you could make is you could, one, subtract a dividend yield called written as basically dividend over the stock price. That's the dividend yield. So if the dividend was $4 and the stock was 100, the dividend yield is 4%. Now you can subtract that. When you calculate the probabilities of up and down, for example, you take 1 plus R, you would subtract the dividend yield in calculating the probabilities. And then you would also, you'd also need to take into consideration when that dividend's paid. The problem with this method is it results in a different dividend payout. The dollar amount varies by where you are on the node. If you're on an up node, the dividend is higher. Then because this bottom is higher, that means this dividend has to be higher in order to keep the dividend yield at, say, 4%. So, and then when you're at the low end of a node, if you're have gone down a couple of iterations, then you're going to have a smaller dividend in dollar amounts. And in the real world, the dividend doesn't vary depending on where the stock price is. Stocks go up and down, the dividend doesn't change because of that. So that's kind of a flaw in that method. But what's neat about it is that you get a little bit of intuition, is that when you have a risk-free asset, it grows at the rate of R. But if it's paying a dividend, it's kind of like negative growth. It's detracting from the growth. And so it doesn't, the asset doesn't grow as fast. In fact, if these two offset each other perfectly, then you'll have a risk-free asset that's really not growing because it's increasing by R, but perfectly offset by the dividend yield. Okay, so that's one method. The second method here is assume a specific dollar amount for the dividend at each node. Okay, specific dollar amount for dividend at each node. Now the problem, this is okay, but the problem is it leads to a non-recombining tree, and so when you start doing more than a couple of steps, it becomes a hassle, and you need to be aware of that. So what you end up having is lattice work that looks like this, and then if you expand to multiple nodes, boy, you get a whole bunch of extra nodes as you go further out. So here you have 4 nodes and you got to account for those, and it's a bit cumbersome. Now when you do this, you leave R and P alone, R and the probability alone under this method. The third method I think is probably the easiest, and that is to reduce the stock price today by the present value of the dividend. So you calculate the present value of the dividend, you take today's price and you subtract the present value of the dividend. Hey, that kind of looks familiar. I should take S, stock price, and subtract that the present value of the dividend. You get S prime, like we have been using. That works reasonably well. You're going to leave R and the probability alone in the calculations. So you're just reducing the stock. This is intuitive, like we've been talking about. If a stock is going to pay a dividend over the life of the option, the stock is going to fall in value And so you take that into consideration right off the bat when you do it. Now what you have to do in the lattice work is keep track of when the dividend actually pays, and that becomes a bit tedious. So those are the three ways of handling dividends. The binomial model that we just did provides plenty of intuition and insight into valuing options, but it produces an approximate option value, not an exact price. The Black-Scholes model produces an exact price for European options. This section of the lecture is designed to prepare you for the Black-Scholes model, which is coming up in the next chapter. Some of the materials presented is presented in the next chapter. So think of this section of our lecture right now as a transition or a bridge to the Black-Scholes model. The Black-Scholes model, as I said a minute ago, provides an exact price, not an approximation, which is clearly a benefit for valuing options, but this precision comes at a cost. The Black-Scholes model is conceptually harder to understand. So what we want to do here in this section is to help with this transition is to look at how money compounds, the compounding of money. So one is compounding of money. The second thing we want to look at here is the random walk of stock prices, or some people would say, to be a little more precise, stock price changes, and I'll talk about that when we get to it. And three is the compounding of volatility. Okay? Or in other words, risk, the compounding of volatility or risk. Now, the compounding of money we covered, you covered in your previous basic finance course. I'll go over that again in the context of the Black-Scholes model. The random walk of stock prices, you may have heard of it, but we're going to go into it just a little deeper and look at what precisely we mean by a random walk. And then it has implications for, the random walk has implications for the compounding of volatility, the compounding of risk, which is something you probably have not seen before in a previous finance course. So the first thing we want to do is the machinery underneath the Black-Scholes model assumes that the number of steps goes to infinity. So we have, remember we had time period, every time period in the binomial, we chopped into a certain number of steps. Here we're going to say the number of steps, n, is going and approaching infinity, which means this whole time period here, this time period is approaching 0. So what we have is, we have a time frame from 0 to t when the option expires. We're not chopping it, the t into two pieces like we did if this was 1 year. And this would be a semi-annual, and this would be another semi-annual period. Or we could have went through and did 4 steps and so on. We have an infinite number of steps all along here. So we're taking the same time frame and just chopping it up into itty-bitty little pieces. In other words, an infinite number of steps. Okay, so let's review what the math means for that. And so let's go back to square one. Remember the compounding of money concepts. You took a present value and you multiplied it by 1 plus r to the n power, and you got a future value in your basic finance course. Now, what happened was in that course, we often assumed that n was 1. So what we did was we chopped the interest rate into a smaller pieces and compounded out. And so when n equaled 1, which was a large component of your previous finance course, if we had a present value of $100 and we had 1 plus, let's say it's 8%, r is 8%, 0.08. Right? And then we divided it by 1 and took it to the 1 power, we would have a future value of 108. So this is our present value, this is our future value. I'll just follow along with this equation here. Okay, no big deal. What you may have hit a little bit upon if you did time value of money is, there's semi-annual compounding. For example, bonds compound semi-annually. And so the formula here just adjusts nicely as follows. You take R, which is always on an annual basis, and it's N divided by N to the N power equals a future value. So all we're going to do now is plug in, if we're looking at semi-annual compounding, N equals 2. And so the math now becomes 1 plus 0.08 divided by 2 to the second power. And mathematically, that comes out to be 108.16. So you make an extra 16 cents if you have semi-annual compounding, because you're compounding this period, and then this period compounds the next period. Okay, so you earn an extra 16 cents out of that. In other words, you're earning 4% here, and then you earn another 4% on the 4%. And that only accounts for 16 cents. So that's a small jump. Now, if you wanted to go annual, annual wouldn't be too bad. You would take $100 and you drop it into a bank account that paid 8% per year, but N is 365. You take it, this would be your interest rate right here for one day. And then you got to take it to the 365th power to compound it for all those days. You end up with 108,328. So $108 and almost 33 cents. So you can see after the first year, you'll see that most of the compounding effects of compounding washes out. So you go from compounding once, you get 108. You compound twice, you get 116, which is a 16-cent jump. And then you go all the way to 365 days, you only get another little more than 16 cents. Okay. Now, we want to ask the question, what happens when we chop this time period here into an infinite number of chunks? How does money compound? Well, you could, and I would invite you to do that at home, is to just change this to say 10,000. Divide this by 10,000, take this to the 10,000 power, recalculate a number. And you can keep doing that. But where do you end on that? Because if you keep increasing N, you're always going to get a slightly different number over here. Well, it turns out that there's a way to simplify that process. It's a little more mysterious, but it reduces the math a bit. And that's by taking the present value and multiplying it by E, that magic number E, which is 2.718. Taking that to the R power, that will equal the future value. So apply it to what I just did. You put $100 in an account. You multiply that by E to the 0.08. Make sure the R is in decimal form. Okay, and then we will get a future value of $108 and a little more, almost 33 cents, a little bit bigger than this 365-day compounding future value number. Okay, so what this number turns out to be is 1.083287. Okay, so this is how you continuously compound a rate in a nice condensed format, simply. And so those buttons are on your calculator. Take a look at them. You'll find them on your calculator. So I got a BA2 plus here. You'll have to hit this yellow button, the second button, to get down to E of X. And then to flip out of E of X, you hit the natural log, LN button. So they're the inverses of each other. E and E to the X and LN, log, natural log, are inverses of each other. Okay. Now, that's the compounding of money that we just explored. Now let's look at the random walk idea. And like I said earlier, you've seen, you may not have seen continuous compounding, but you know what compounding of money is. You've seen that probably too much when you took your basic finance course. But what you didn't know is that volatility ends up compounding also. And in order to understand how volatility compounds out, we need to look at this random walk model, because the random walk model is underneath the Black-Scholes model that we're going to start up in the next chapter. Okay, and the random walk model of stock prices. So it's the random walk model of stock prices. That's slightly sloppy because we're looking at the random walk model of stock price changes. What follows a random walk is the changes in stock prices, not the actual stock price. So that, you know, if we start at $100 stock price that equals S, or, you know, S equals $100, and let's say it's right here graphically, then the change in the stock price over the next minute, so this is time on this axis, the change, you can think of it as, you know, think of it as a normal distribution here. The change can be up or down, and it'll have varying magnitude. Most likely going to be a small change, but it could be a very large positive change. It could be a large negative change. So, in the way I have this flipped here. So, keep in mind that it's the changes in the stock price and not the actual stock price that is a random walk. And so what we're saying is these changes are random. Okay, now, let me give you a bit more context. So before I go further, let me give you a bigger picture of where we're going with this. Before I actually show you a graph of the random walk model and how it compounds volatility, let me show you a mean reversion model. So here we have a mean reversion model graphically for a stock price. So this right here, to be clear, this is the stock price, not the change, the stock price. And let's say we start at time 0, we can go to T is 4 in this case. Let's assume this is 1 month, so we have week 1, week 2, week 3, week 4 here embedded in this graph. And this is mean reversion. You can see mean reversion because what happens is when the stock price itself is above average, it means that, you know, soon afterwards it's going to be below the average. And what is the average? Well, the average is this line right here, right down the pike here. Think of that as the mu for stock price, you know, the symbol we use in statistics for average or a mean. And so this is mean reverting. There's some type of tendency causing the stock price to revert back to its mean, and then it may overshoot, and then it may come back down again, but it'll overshoot again, and so on and so forth. But so it keeps crossing its mean. So you see that. Now you could think of this as look, you got a distribution here, and you got a distribution here for this week, and I'm trying to draw it the best I can. But assume these distributions, and I didn't draw it very well. But assume the distribution for each week has the same amount of spread or the same standard deviation in variance for each distribution here. And so you can model that as mathematically, you can say, look, it's the variance of week 1 plus the variance of week 2 plus the variance of week 3 plus the variance of week 4, right? And what I'm getting at is I'm trying to calculate the variance for this whole time frame. So you have these variances, but they're not independent, because when you tend to be below average here, you're going to be above average here, and so on. So that then you have to subtract off the covariances between week 1 and week 2, and the covariance between week 1 and week 3, and so on. So what you have here is that the variance or the volatility of a month equals 4 times the variance of a week, right? But in order for this to equal, you average out, you take the average of those 4 volatilities. The difference, there's no difference between the volatility of a month versus the volatility of a week. And we have this relationship. That is a mean reverting process. Notice there's a ton of predictability in here. And so when you're above average, you're likely to be above. When you're above average, the next period you're likely to be below average, and so on. And so if you're above average this week, you're going to be likely below average the next week. That's negative covariance, and negative covariance offsets each other. And so that's what's happening in the math here. Things offset. Now, stocks can't follow this type of process. This would be like shooting fish in a barrel for traders in the stock market, because it would be easy predictability. You would just tend to sell here when the market's above the average or above the mean, and you'd buy when it falls below the mean, knowing that it's going to go above the mean in a few minutes or days or weeks, and so on. And so that's a ton of predictability. The stock market can't follow that process. The stock market has to follow, or should follow, something that has more randomness in it, and that's where the random walk model comes in. This is an example of a random walk stock price. A stock price following a random walk. So we got a stock price here. We're looking at a 1 month time frame. We got each of the weeks listed like before. But notice what's going on here. In a random walk, we have, let's look here. We have a mean for the first week that's here. And then we have for the second week a mean that's here. And then we have a mean for the third week that's up here. And then the fourth week, the mean is here. So you have a mean that keeps changing. That's part of a random walk model. It tells you that you don't really have a solid mean. For this entire month, you have a mean that keeps moving all over the place. And that's what makes finance math so difficult, is trying to deal with this moving mean. Sometimes it's called a non-stationary mean. The mean is not changing, or is not staying in place. So what you have is we may have a standard deviation each of these periods, and it's hard to graph this. Just work with me here. So we may have the same distribution in each one of these weeks, the same variance each week here, okay? But notice what happens is that's the variance for each week is the same. But what happens when you look at the variance for the entire month? Wow, the variance of the entire month is way bigger, because if you wanted to do a variance of the entire month, you would put a mean probably right down the middle here, and you'd have a standard deviation. I'm just going to draw it right over top. You'd have a standard deviation that kind of looked like that. It would certainly be a lot bigger than these individuals if I tilt these individuals weeks that look something like that. So wow. So what you just seen graphically here is that under a random walk model, you can estimate this quite easily in Excel. There's lots of lots of studies on how that's done and how to implement this in Excel. But you can easily do this and see that, wow, okay, volatility, it is compounding. This does look like a stock price, or even a commodity price in some cases, or oil. And you can see that the volatility is actually greater. In other words, the risk over 1 month is greater than it is for each week. So what's happening is, this is what I'm saying is reflecting the compounding of volatility when stock price changes follow a random walk. And what the slang would be is stock prices follow a random walk. So mathematically, what we have here is this. If we want to look at the variance of a month, that's going to equal the variance of the first week plus the variance of the second week, plus the variance of the third week, plus the variance of the fourth week. Okay? And so since this is a random walk, the covariance terms, how does week 1 behave relative to week 2? How does week 1 behave relative to week 3? And so on. All those covariance terms are 0, which means there's no correlation from one week to the next. There's no correlation one week to the next in this graph. And so all these zeros cancel out. And so what we have is, if we assume that the variances are the same each week, we have 4 times the variance of the average week. Okay, I'll call it W here. So the variance of 1 month is 4 times the variance of a week in that case. And I'm just multiplying, because I got 4 terms here and they're all the same amount. I'm just multiplying it by 4. Now the standard deviation of a month will equal the square root, so take the square root of both sides, of 4, and then you get the standard deviation, but you get this adjustment here. These are not equal like they were in the stationary process. In the stationary process that I showed you here, in other words, the mean reverting process, there was a 1-to-1 correspondence, but this is not 1, this is actually 2. And what this boils down to generically is the variance of a month is the square root of time times the standard deviation, or I should say the volatility of a month equals the volatility of a week times the square root of time. So what you're going to see in a lot of the work in the next chapter when we cover the Black-Scholes model is you're going to see an adjustment for the volatility. And it's going to look something like this. You're going to see this term pop up in a number of different places. And all we're doing is we're adjusting this is an annual volatility, meaning an annual standard deviation. And we're adjusting it for the square root of time. And the reason that we're doing it is, again, the Black-Scholes model assumes that stock price changes follow a random walk. And if it is a random walk, volatility compounds over time, and it compounds at the square root of time. So T will be, as it has been, the fraction of years that over the life of the option. So the fraction of a year that an option is alive before it expires. Before we begin the Black-Scholes model in the next chapter, there's one more important transitional concept that I think you'll find interesting, and it will tie directly into what we just learned about the compounding of volatility. I want to go back to the comment I made earlier in this lecture about the underlying selection, the underlying choice of U and D in the binomial. So if you recall, I said U equaled 1.171 and D was the reciprocal of that, and that equaled 0.854. So we had the up and the down movement was up was 1.171 and down was 85% of where we started with. And so I want to get at, where did that number come from? How can we tie that into volatility? Well, it's not hard. It turns out that U equals E to the sigma square root of T over N. Okay? And so there you have the compounding of volatility adjusted for each step. And that's what this part does. It adjusts for each step. And the volatility here, this standard deviation, is on an annual basis. So annualized, so it adjusts for that fraction of a period relative to a year. And E is that compounding process. Now this whole thing equaled 1.171. Okay? So what we're doing is, what you can see immediately is that the size of this step up you put a line here. The size of this step up and the size of this step down, in other words, volatility, is a function of this standard deviation. And so if we solve this for sigma, then we can figure out what is the underlying volatility here. And so that involves taking the natural log, as I told you earlier, that the inverse of E is the natural log. So take the natural log of both sides. So if you take the natural log of both sides, the natural log of 1.171 is 0.1579. Okay? The natural log of this right here is simply sigma square root of t over n. Okay? And so what we have is, we have one equation, one unknown. We got rid of that exponent because we're trying to find a... So here's a trick in math, and you may not realize this, but normally you're used to solving x in algebra with algebra, solving for x, but basically the x is now an exponent, and when x is an exponent, you generally have to you're looking at things that are nonlinear, and you probably should be taking logarithms because natural logarithms will make things linear, and when things are straight lines, linear, it makes the math so much simpler. So you're going to have to exercise the LN button on your calculator and to calculate this 0.1579. Now, we don't know what sigma is, but we do know what T is, and covers a 1 year, right? Remember, it's 1 year, and we want to figure out the fraction of a year that we're addressing here. And so in the binomial that we did a two-step binomial. So we take it to the 1/2, the square root of 1/2, where this is 2 steps. And then that equals 0.1579. And so when you solve this, you come up with sigma equal to 22.31. Okay, and so what we're doing here is we're saying, look, an up movement is a function of E to the 0.2231, okay, times the square root of 1/2. And we're saying the D movement, which is the inverse, can be written this way. E is minus 0.2231 square root of 1/2. And so, as I said, the size of these up movements and the size of the down movements are a function of this volatility that's built in. So I introduced the U and the D. I just gave you the numbers, but now I'm giving the intuition that those size of those ups and downs are a function of the volatility of the underlying stock. So keep that in mind. It's the volatility of the underlying stock is 22.31%. I debated when I produced this video, where should I put the coverage of the software that comes with the text? Where do I cover that? Should I cover it up front or at the end? And I think it's best that I cover it at the end because it's only towards the very end I compute the sigma, as I'll show you in a minute, the standard deviation, how you get the standard deviation from the U's and the D's and how to extract that. And so I'm going to use that information in this video. The software that comes with the textbook and is found on Blackboard, I have it under Blackboard under a tab called Software. And in this, it's an Excel spreadsheet that's there. And what that does is it computes binomial option pricing models, puts and calls, American and European. And it also does the Black-Scholes model, which is in the next chapter. And so this is an excellent opportunity for you to confirm your work when you're doing homework or you want to recalculate something, you're not sure if you did calculations right. Plug the numbers in here, hit the run button, and things will pop out automatically for you, and then you can interpret them. Now, it's a great opportunity for your homework, to work on your homework, but you can't use this for a quiz. You're going to have to be able to compute things by hand for a quiz. Now, In chapter 4 in the video, I had an option where the stock price was 50, the exercise was 52. It had 1 year to expiration, and these are all inputs on the left here. And then I had a standard deviation that we just calculated to be 22.32%. Okay, so I hesitated where to put this part of the video in the overall video on chapter 4. Where do I put this section? And I put it in the end because it's towards the end that I show you how to compute this standard deviation. So it kind of makes sense. This is at the end. Now, the risk-free rate was 8%, and the risk-free rate is a discrete rate. It's only compounded once. It has the ability to put in a continuously compounded rate like I showed you, and then you'd hit the continuous button here, then some of the numbers would change. But we're using discrete like we used in the binomial when we did our work. Input that information. You can put dividends in here. You can put it in one of two ways. You can put a dividend yield in. See, it's a percent here, which in our case was 0 at the time. Or you can have zeros here for the actual, or you could put numbers in for the actual dollar amounts of the dividends over the life of the option, and it'll automatically compute the present value of the dividends and adjust the option value for it. So once you get this information in, you're going to come over here and make sure, since we did 2 steps, I'm going to put 2 steps. Now, if you look here, you can go up to 5,000 steps, and I'll show you what happens when you're running many more steps, how the model changes. So we hit the run, and when we hit the run button, here we have the option price for the European call. That's what we first worked on. And if you recall, we came up with a price of $5.28. And this is coming up to $5.20, almost $5.24. And the reason is, if you go back to what we did in those 2 steps, we must have done 50 calculations, and we rounded. I rounded H, I rounded stock prices, I rounded call prices. There was lots of rounding, so that's what I chalk it up to be. We had about a nickel in rounding, maybe 4 cents in rounding. The put that I calculated was $3.35 for the European, and that's within that's like 3.5 cents difference than what we had before. Now here what we have is, and this slightly, I had to break into the code that came with this software. The authors had for H, the hedging ratio, they had some strange average that they don't explain in the textbook, and I've never seen before, some type of average. And what I did was I broke into the code, and I put this is the H for the first step in the European. So in the H in the first step, the hedge ratio was 0.41, and then for the put it would be negative 0.58, almost 0.59. Okay, so that is for the first step. And I broke into the code. You can go into this code. If you go to developer up here, top, hit developer, come over to the left and hit Visual Basic, you can jump into here's the code. Here's all the code that did all the calculations behind the scenes. And, look, if you look carefully here, I'm using the max of 0, and there's the X strike price minus the stock price times up movements twice and so on. So, right here you can see I'm using the maximum of 0, or really the payoff at expiration. So let's bounce out of this. You come back out by hitting the X here for Excel. We're back in here. So now the way I have these 2 H's, each H works this way. It's no matter how many steps you have in this model, it's simply the first step. Okay. And then notice, what else you want to notice here is that look at the call, the European call and the American call price. They are identical. Remember, I told you, you don't get, you got extra optionality with an American call, but it's not worth anything because all you do is when you exercise early, you're paying the exercise price early, which doesn't make sense because you're losing that time value of money associated with it. So you're better off holding the option or exercising it. And so the European call and the American call have the same price, and they have the same H, or what's often called delta. Okay. Now, we also value the the American put. And if you recall, we calculated the American put to be $4.14. We're off about 3 cents. We're off about 3 cents. And notice, and that's because the put is worth, the American put will be worth a little more than a European put. And notice also that the H is a little different because that H is taking into consideration that optionality that I showed you at the first node, the first bottom node. If we recall, the price of the European would have been $7.30 on the first down node. But when you look at the exercisability, the exercise money that's available, the intrinsic value at that node for the American, it was $9.30. This is picking up and reflecting that. So normally, if you come up here to the European, you would see that the sum of the absolute values of the H's will add up to 1. But it doesn't necessarily add up to 1 for the Americans because of that optionality issue where you have to go through each and every node to see what's more valuable, the European or exercising the option right then and there. So the other thing I wanted to mention here is take a look at the gammas and thetas. We have not talked about that yet in Chapter 4. Well, we're not going to cover it in Chapter 4. It's not discussed in Chapter 4. Very few textbooks talk about gamma and theta in the binomial context. It's here if you want to look deeper into it. But we will cover these, these are called the Greeks. There's measures of sensitivity. We'll cover them in the context of the Black-Scholes model, which is coming up in the next chapter. And in the next chapter, we'll cover this delta, we'll cover this gamma, theta, vega, and rho. And what these guys do is they measure sensitivities of the calls and put values for a change in the stock price, a change in delta, which may not make sense, but it's a measure of curvature. Remember the option price line is slightly curved. This will measure the curvature. Theta is how sensitive the option price is to a change in time. Vega, it's technically not a Greek letter, but it's about volatility and how if you change volatility, how much does the option price change by? And rho is how much the option price changes by a change in interest rates. All will be discussed in Chapter 5. So one other thing, like I referred to you a minute ago, I said, look, this is the two-step binomial. Let's ramp up the number of steps, and what you will see is we will come up with an exact value for these European values. These put and call prices will now become nearly exact. Because we're going to have, it's certainly not an infinite number of steps. So if we take 500, for example, take 500 steps, run the binomial model. Look at the wheels spinning. It's thinking, it's thinking, it's thinking. There we go. Now notice we're really close to between the European call on the binomial versus the Black-Scholes model. We're really close with the put also. Okay, now the Black-Scholes model only does European options. It doesn't do American. That's a much more complex model. As you can imagine, it was kind of, you imagine trying to program something that captures the optionality of it. It's kind of a bit of work to do this for me in breaking into the code. So now, so these, when you start getting up to these higher numbers beyond 2, your H's aren't going to work. The H's are going to work for 2. So you can check your work if you do a two-step binomial. You'll get the right H's and the right deltas in there. So that's a summary of how to use this software. It's quite valuable. So the point is, there's a lot of calculations. I don't want you to get overwhelmed by them. You can check your work pretty quickly and catch where your mistakes are up front, and this will really help you out.